Hello students, welcome to EEEE lecture number 35A. Alright, so yesterday we have started with this is EEEE lecture 35A live, and the date is 17/4/24. Let me turn on the full screen. Okay, so we will solve two numericals on diode equation. So I've already have the statement over here, no need to write the statement. Find the forward current in a silicon diode. That means we have to find IF. Alright. At a forward voltage of 0.6 volt. So what do you mean by forward voltage? VD. Or this is IF or ID. Correct? So VD is given as 0.6. Reverse saturation current of zero point 0.1 microampere. So IS is zero point 0.1 microampere. So just write this constants. Then the temperature is 27 degrees Celsius, and if a reverse voltage of 10 volt is applied to the diode, so here my VR is 10 volt. Find the reverse current flowing through the diode. So we have to find IS in the next part. Okay. So for the first part we require only this much information. Okay. Can we start? You have written this. So one thing you remember, for T equal to 27 degrees Celsius, you have to remember one constant which is called as thermal equivalent of voltage, Vt. So Vt is 26 millivolt. This is, you have to remember. Alright. So let's start with the solution. I hope it is clear. So first case we have to find ID. So first here is the proof that Vt is 26 millivolt. No need to write that in the exam. This is for one time reference for you all. It is only for reference. Okay. So directly substitute Vt equal to 26 millivolt over here. Then start writing the diode equation. ID is Is times e raised to Vd upon eta Vt. Now since it is a silicon diode, so for silicon eta you take it as 2. Okay. So now actually we required a value of ID. So first calculate Vd upon eta Vt. How much is the value? So Vd is around how much? 0.6. Eta is 2 and this is 26 millivolt. Find this number. Okay. So tell me what is the number? You have to solve and tell me what is this number. Vd upon eta Vt. zero point 0.6 divided by 2 into 26 millivolt. Quickly solve because we have to cover more important topics. How much is the value? Hello. 0.6 divided by 2 into 26 millivolt. How much do you get?
11.5.
Okay, 11.5. Then in the next step, ID is um, this is reverse saturation current, zero point 0.1 into 10 raised to minus 6. E raised to 11.5 you do. In the bracket you put e raised to 11.5 minus 1. So tell me the value of ID now. Put it in your calculator. You know how to do e raised to something, right? This e raised to 11.5. This is 11.5 as you said. So calculate ID. How much it is? ID. 0.1 micro into e raised to 11.5 minus 1.
9.87 into 10 raised to minus 3.
9.87 into 10 raised to minus 3 amperes, right?
Yeah.
So it's approximately 9.87 milliamperes, correct? Others are also getting the same answer?
Yes.
Okay, great. So that is your answer. Now, in the second part, Reverse voltage is given as 10 volt. So VD is minus 10, correct? So if you substitute ED as VD as minus 10, calculate this number x3, I mean e raised to minus 10 2 into 26 millivolt. This will be very, I am sure this will be very very close to 0. Calculate this number. If x3 is 0, I mean if this number is 0, then your value of ID will be same as IS, minus of IS. Calculate it. So ID, is it 0? E raised to minus 10 divided by 252 millivolt. Very very small number it will be, into 10 raised to minus something, I guess. How much did you get? Hello?
3 into 10 raised to minus 84. It's very small.
3 into 10 raised to,
Minus 84.
so it's 0. Better to say it's 0. So if this is 0, so 0 minus 1, it will be minus IS, right? So ID will be equal to minus 0.1 microampere. Please write down the answer. And this is the reverse current in a silicon diode. This is the value of reverse current in the silicon diode. This is the value of forward current in the silicon diode. Alright. So have you completed the numerical, everyone? Can we just move on to the next one? Okay.
Yes, sir.
Alright. Let's move on to the next one. In the second numerical, reverse saturation current of germanium diode is given as 5 microampere. So IS is given 5 microampere. Temperature is 27 degrees Celsius. So VT will be 26 millivolt. You have to assume this value. Forward current is given as 25 milliampere, and we have been asked to find forward voltage. Okay, so actually here we have to find this value VD. All right. So what we do is we open this bracket and we take IS on the left hand side. ID plus IS is equal to IS times e raised to VD upon eta. Eta is 1 because of germanium. So eta VD upon VT. So e raised to VD upon VT is equal to 1 plus ID upon IS. So please calculate this number. 1 plus 25 into 10 raised to minus 3 divided by 5 into 10 raised to minus 6. How much is that y1? 1 plus this. How much is the value of y1? Come on, tell me fast. 1 plus 25 milli divided by 5 micro.
5001.
So now calculate natural log of that. 5001. How much is the value?
8.51.
8.51. Okay. Now multiply this number with 26 millivolt. So tell me the value of VD. That was the value of VD. How much it is?
0.2212.
Volt. So this is the value of the forward voltage for the germanium diode. Okay. So these are the small numericals which can be asked in the exam for related to diode, PN junction diode. So we have seen so far in PN junction diode its construction, working in zero bias, forward bias, reverse bias. Okay, and we have also seen the IV characteristics of the Zener diode, correct? And now we'll see one last topic, temperature effect on the IV characteristics. So can we go to there? Yeah. Okay, so let's open that PDF. So this is 35 number B. Write down the topic, temperature dependence on the diode IV characteristics. So temperature actually significantly affects the diode IV characteristics. Okay, and which are the temperature dependent parameters which are very much disturbed by this? VT, thermal equivalent of temperature, voltage, and this is IS, reverse saturation current, are heavily temperature dependent terms. Okay, so this increase in temperature will result in increase in thermal activity inside the PN junction, and that will decrease the diode resistance, which will influence both forward and reverse characteristics. Okay, so let's go to this now. So this is a fact which we don't have to prove, that the diode forward voltage decreases by 2.5 millivolt per degree rise in temperature. So write down this one which I am tick marking. Diode forward voltage decreases by 2.5 millivolt per degree Celsius rise in temperature. So let's say the temperature has risen by 10 degrees Celsius. So how much is the forward voltage will decrease by? 25 millivolt. Okay. So diode forward voltage decreases by 2.5 millivolt per degree rise in temperature. Can we go on to the next one now? Okay. So these are all the effects which okay, next effect is this effect on the temperature on the reverse saturation current. So the fact is the reverse saturation current and the breakdown voltage increases with increase in temperature. So this fact you have to write, the reverse saturation current doubles every 10 degree rise in temperature. So this is my reverse saturation current for 25 degrees Celsius, and it becomes almost double at 35 degrees Celsius. So let's say this is at 5 milliamp, 5, let's say around 50 nano. This becomes around 100 nano at 35 degrees Celsius. Okay, so write this. The reverse saturation current gets doubled for every 10 degree rise in temperature. This is another fact. So PN junction is output characteristics is heavily temperature dependent. Completed the second, return to second fact. The reverse saturation current gets doubled for every 5 degree rise in, for every 10 degree rise in temperature. Now, we'll see the overall effect on of temperature on the diode characteristics. So, I have drawn two curves. One is at 50 degree, one is at 25 degree. As I've already showed you all, the forward voltage VD1 and VD2, here it is, VD1 and VD2 decreases with increase in temperature. So if I operate at 50 degrees Celsius, I'll have a lower forward voltage. And if I have a 25 degrees Celsius, I will have a higher forward voltage. And also the forward current correspondingly, let's check at one point. Forward current also increases with increase in temperature for the same voltage. Okay. So forward current increases. This is another fact. Now next, reverse current increases with increase in temperature, that we have seen already. It gets doubled almost, right? Also the reverse breakdown voltage increases with increase in temperature. Here it is. So if you operate at a higher temperature, the reverse breakdown voltage will increase with it. So these are the effect of temperature on the diode characteristics. So if you are noting it down, please note it down fast, quickly. There are these four effects. Forward current increases with increase in temperature. Forward voltage decreases with increase in temperature. Reverse breakdown voltage increases with increase in temperature. And reverse current increases with increase in temperature. These are the four effects. So if they ask you in the exam, write a short note on temperature effects on the diode IV characteristics, you have to write this much. Okay, mostly it will come as a short note. So remind me today at the end of the lecture, before I leave, I'll share you the questions. module wise questions which I prepared just by looking at the syllabus, nothing else. Okay, so I'll share that information at the end of the lecture. Okay, is this completed now? Can we start with the actual topic now? Yeah, students. Hello.
Yes, sir.
Okay, let's start now. Let me show it to you what we have in our curriculum related to. So basically whatever we have completed, I'll mark in yellow color. So we have completed the PN junction diode up till here. Now we'll start with application as a rectifier, half wave with resistive load, full wave center tap, bridge rectifier with resistive load, with the parameters such as ripple factor, rectification efficiency, and transformer utilization factor, and filter circuits. So let me uh, copy this part. So this much part is pending. We are trying to cover this today. So let me start with a new page. Yeah. So that is a topic which we have to cover today, right? Okay, not this one. Yeah, this one. Okay. So we'll start with half wave rectifier with resistive load, application of rectifiers part. Okay. So this is lecture number 35 live. Let's start with application of, and this is module number 4.1. Okay. So this is 4.1 which we are doing. Then 4.2 is Zener diode, its construction and working, and application of a Zener as a voltage regulator, and then light emitting diode and photodiode. That are pretty simple ones. Okay, let's start with this. EEEE lecture number 35 live, 17/4 2024. So please write along with me. If you are understanding something for the first time, then it's okay, or else you can write along with me. Now, basically, what we need to do is from this module number 4.1, we have to start with application of diode, that is rectifiers. Okay, so we have a main topic called as rectifiers, which is the application of a diode. Here we'll study three types of rectifiers. First is half wave rectifier. Yeah, if you can listen, it's fine. Then full wave, center tap rectifier, and then you have third category as bridge rectifier. I hope you have heard of these terms before, or you have studied this ever before. Rectifiers in details? Yes, no?
Yes, yes, sir. Yes.
You have studied this. Okay, so let's go a little faster. You have studied with a resistive load.
Mm, I don't think so, sir. Sorry.
Okay, so we'll study all these types of rectifiers with R load only. Okay, you don't have any other load. And
Okay.
secondly, we'll only study the parameters. Have you studied these parameters before, which I am writing over here? Will determine the ripple factor.
No, sir. Sorry. Sorry.
Yeah, yeah, okay, fine, no problem. At the outset, I'll believe that you'll have never heard of this before, and then accordingly, I'll teach you. Rectification efficiency, and then transformer utilization factor TUF. So we have to derive these parameters for all these three rectifiers. So there are around, good news is for full wave center tap and bridge rectifier, the parameters derivations are similar. Only for half wave rectifier is different. So we have to derive it twice, and it's only with R load. And then plus we have to study filter circuits. Now in filter circuits normally we have RC filter, so we will study only capacitive filter, and that will complete your module number 4.1. Okay, this is the summary. Now, for the diode, what do we information we require? So this is the symbol of the diode. Okay, this is the forward voltage VD. Diode is called as D, and the current flowing through the diode is ID. Okay, when the diode is on, we'll assume it. Normally, it should behave as a, let's say, a battery of zero point 0.7 volt. Yes or no? But ideally, we'll assume it almost it's like a diode is on, it will behave as a short circuit. So this is diode is on or forward bias. It will behave as a short circuit and ID current flows. Okay, yes or no? And if this is what we assume, the reason being we assume it as a almost like a closed switch is we are dealing with rectifier. So there we are dealing with around voltages which are very much greater than zero point 0.7 volt. Okay, so in that we will be assuming that diode is behaving as a closed switch, and then we'll study the analysis. Okay, then the next case when the diode is off. In next case when the diode is off, when is the diode off? When we apply reverse voltage to it. Yes or no? So if you apply plus here minus here VD, diode becomes off. Yes. And when the diode is off, you replace it with a open circuit. So diode is reverse bias. It behaves as a open switch because current doesn't flow, very less current flows, so it behaves as an open switch. This is what we have to remember, and this diode is your PN junction diode. Okay, so with this information, can we start with rectifiers now? Everyone ready?
Yes, sir. Yes.
Okay, okay, so let us start with rectifiers. Yeah, so write down diode application, rectifiers. As I've already informed you all, we have three types of rectifiers. You know all the three types now. Half wave rectifier, I am writing in short form. Then we have full wave center tap rectifier. Then the third one is, what was the third one? Bridge rectifier, correct? And all of them has to be studied with respect to only with resistive load. That is very important. Okay, so you can write along everything from now on. And generally, if they ask you a question on rectifiers, they'll ask you one of these questions. First will be you have to know the circuit diagram of the particular rectifier. Okay, for any, I'm telling this for all the three rectifiers in general. Next, you have to explain the working of that particular rectifier configuration. Next, input output waveform with respect to time. Next, you have to do the analysis. Now, under analysis, you have various things. First is we have to find out V out average or I out average from the output waveforms. Then you have to find out V out RMS value or I out RMS value. This is the analysis part. Then we have to find out rectification efficiency given by eta. Next, we have to find out ripple factor R. And next, we have to find out TUF, transformer utilization factor. Okay, this is rectification efficiency, and this is ripple factor. So for any, in this matter, for all the three types of rectifiers, we have to find these things. Point number 1 to 4, 1 to 3 in circuit diagram working input output waveforms, and from analysis part, point number 1 to 5. Alright, so can we start with half wave rectifier with R load? Let's start the first one. Write down half wave rectifier with our load. Okay, so first of all we'll see what is the outcome, what we achieve over here. So half wave rectifier, I'm calling it as HWR. So here we have an input signal to a half wave rectifier. I'll show it to you what it will do to that. So this input signal will, let me draw this dotted line, same thing. Okay, let me draw one more cycle of it, because one cycle is not sufficient. So one, two, three, yeah, here it is fine, like this, same only it is. So what it will do is, only half the cycle it will rectify, remaining half will be as it is, will be grounded. So the output of this half wave rectifier will look like this. Only when it is positive half cycle it will follow the input, for negative half cycle it will be 0. So this is half wave rectified output. This is your rectified output, and we have to analyze this part. Okay, so this is what a half wave rectifier do. So let's first start with the circuit diagram. So draw the circuit diagram first. A part, circuit diagram. So first we have a AC main supply that has been passed to a transformer. So this is your transformer primary winding, and there you have your secondary winding of the transformer. Okay, so let me show it to you. First, this is AC mains. What are the specifications of AC mains? It's single phase, it's 230 volts RMS, and it's 50 hertz. These are the specs. So AC mains is applied to the transformer. This is actually called as a step down transformer. Well, what is the job of a transformer? It has two jobs. It will either step up the AC voltage or step down the AC voltage, means it will convert high AC voltage to low AC voltage. In this case, it is doing that. So step down. Okay, it has two prime windings. N1 is the primary winding, N2 is the secondary winding. So let's say, for example, this winding is N1 is to N2. It is in the ratio 10 is to 1. So what will be the primary voltage look like? 230. So what will be the secondary voltage divided by 10 times? That is, this is 23 volts. So here 23 volt will be available. Okay. So this signal we call it as VI. Okay. So VI will be a low version of AC. I mean low amplitude of AC signal. Okay.
हेलो एक्सक्यूज मी सर सॉरी
Yeah.
ये जो स्टेप डाउन ट्रांसफार्मर है सर वो टेबल फैंस और उसमें यूज़ होता है ना जस्ट टू बी श्योर
Where?
टेबल फैंस है वो पार्टीज और उसमें वो बड़े स्टैंड वाले फैंस रहते हैं कनेक्टेड टू योर हाउ टू एक्सप्लेन दिस सर
Yes, yes, yes. I understood. I
हाँ
understood. That which
हाँ
moves around.
हाँ यस यस सर वो हाँ वही सर एग्जैक्टली बस उतना ही समझ रहा हूँ
Ha.
बाकी नहीं समझ
This is there. You have done this in your lab also. In the lab, you have used a center tap transformer, which was a step down transformer only. Okay.
ओके सर
So this is in the ratio 10 is to 1. So here
ओके
you get 230. At the secondary, you will get 23. So
अच्छा
VI over here is around 23 volts. Just an example.
यस
So
सर
by the ratio of 10, it's reducing.
ओके ओके
अगर 248 हो, it will reduce to 24. But this is AC. Still, it is
ओके सर
AC. This is also AC. This is also AC.
अच्छा वो डीसी नहीं हो जाता सर वो
No, 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 not DC.
ओके ओके
Now, what we do is we connect it to a diode,
ओके सर
and this we require some load also, so that, we have a resistive load, R load, and this we ground it, and this we call it output. That's it.
ओह ओके
So,
अच्छा
have you studied this kind of a circuit?
नहीं एक्चुअली सर वो जेडब्ल्यू और वो सब में 11th 12th में बहुत ऐसा इंटेंस हो जाता था वो इसलिए याद है
Okay, okay. But this is the circuit diagram. So please draw the
Okay,
circuit
okay,
diagram, everyone.
okay. वो एग्जाम्स में आएगा सर, ड्रॉ द सर्किट डायग्राम.
हाँ, that's what I've explained ना. ये देखो ये
ओह ओके.
9 points
ये
लिखा है.
न्यूमेरिकल्स नहीं आते सर?
नहीं, there
ओह
are
सेम सेम.
fortunately there are no numericals for rectifiers.
ओके ओके ओके. हाँ ओके सर, मतलब थ्योरी ही आता है पूरा,
Yes, theory.
लाइक कंस्ट्रक्शन वर्किंग वो सब. ओके
Yeah.
थैंक यू.
Okay. Fine. So please draw the circuit diagram. Now, mathematically, how do you represent a sine wave? Anyone? Vi is equal to Vm sine omega t. Agree? Yes or no? This is secondary voltage. What is Vi called as? Secondary voltage of transformer. Correct? Yes or no? So this is Vi. It has an amplitude of Vm plus Vm and then minus Vm, then again plus Vm, like this. So this is Vm, this is minus Vm. Agree? This is pi, 2 pi, and this is omega t. This is 0. Okay. So for one half cycle, it remains in the positive half cycle. That is, this is positive. Then again it goes to negative half cycle. So let me change the color and show you the negative half cycle, which is green in color, like this. Okay. So it will remain for a brief interval in the positive half cycle, then it goes to the negative half cycle. That's how our AC signal looks like. Okay, so this is positive half cycle indicated by plus sign, this is negative half cycle. So alternatively it keeps on going, switching over to negative and positive half cycles. Okay, can we start with the working now, everyone?
यस सर यस.
Now remember this Vm and plus minus Vm, it's actually around acha, this if 23 is the RMS value, what is the Vm value? What is Vm in terms of RMS? VRMS.
इंटू टू इंटू रूट टू हो जाता है या फिर डिवाइड होता है सर, शायद निकालने के लिए.
Only two options are there.
ओके.
Anyone knows what's the relation
into
with?
root 2.
नहीं नहीं, what? Vm is root 2 RMS. ऐसे ही होता
Yes,
है,
sir.
or it is divided by root 2,
Multiplied by root.
multiplied by root 2. So this is root 2 times 23 volt. So कितना हो गया ये, around 30 volt हो गया. हाँ, 1.4 ना, around 30 से ऊपर ना. What is 23 root 2? How much? Tell me fast.
32.52.
Okay, so this much is the amplitude of this AC signal. Okay, now let's consider this in two cases. The same diagram we'll study in two cases. So let's say during, give you positive negative, yeah? This is positive half cycle, negative half cycle. So during positive half cycle of input. So remember, now we are talking about positive half cycle of input Vi here. Okay, so can I say here the diode is on now because you are applying positive voltage over here and negative voltage over here, right? So is the diode on? Yes. Yes, now diode is forward bias, right? So during the positive half cycle of the input, diode D1 is forward bias, that is on. Yes or no? Hello. At least, I mean, you agree on this?
Yes.
So we'll redraw the circuit, but now we'll replace the diode with a short circuit. You understand why? So this is V out, this is RL, this is Vi. So now tell me what will be, this is V in. So V in and Vi are different things. And this is diode 1 on. So will the current flow in the circuit? Let's call that current as I out. Okay. Now diode D1 is on. What will be the V out voltage now? Tell me. Looking at this circuit, V out voltage will be equal to VI, right? So we can say here output follows the input Vi, secondary voltage of the transformer. Yes or no? Because this V out is parallel to Vi. See here, this Vi, since this diode drop we are assuming 0, ideally it should be zero point 0.7, but it's 32 volt we are talking about, so it's almost negligible. So Vi will be equal to V out. Agree? And the current starts flowing. Can you tell me what will be the I out formula? I out here, it will be V out upon RL. Agree? Hello?
Yes, sir.
Okay. So if you have a signal like this, let's say I am drawing my dotted line, positive half cycle, then negative half cycle, and then positive half cycle. This dotted line is my Vi. So what will happen in the positive half cycle? Tell me. It will follow the input. So this is V out. So during the positive half cycle, it will follow the input. Okay. This is what a conclusion is. Are you understanding now? Now, what happens in the negative half cycle? In the negative half cycle, the polarity changes, right? This plus becomes minus and this minus becomes plus. So here also polarity changes. This plus become minus, this minus become plus. So now the diode will become reverse bias. And when the diode is reverse bias, it is behaving as a open switch. Yes or no? We have studied now. So during the negative half cycle, the diode will be off. Okay, so let's write this down. So case number 2, I hope you are following. During the negative half cycle of input Vi, diode D1 is reverse bias, therefore it is off. Okay, off means here we are applying minus voltage here like this. This is Vn. The polarity reverses, right? Here also it becomes minus, this plus. So the diode becomes reverse bias. It is behaving as an open circuit. Will the current flow over here? Tell me. Will I out flow over here in this circuit? In open circuit? Yes or no? Simple, tell me. No, na? I out will be 0 because diode is off. Okay. If I out is 0, what about V out? V out is I out into RL. That also will be 0. Okay. But if I want to calculate diode is off, that is for sure. So here we assume that diode is off. But what about the voltage across the diode? VD1. Is VD1 0? Anyone? Hello? Can you answer this question? Is VD1 0?
No.
No. How much is VD1? Voltage across the diode. It's equal to minus of V. This is not V in, this is VI. Correct, na? So it will be minus of Vi, which is minus of Vm. This is called as peak inverse voltage or peak inverse rating of diode. Sorry. So let me explain you what is PIV rating. So when the diode is off, matlab, let's see, when a diode is off, it has to withstand a reverse voltage of Vm. Okay, meaning across the diode. So if this is the diode, okay, and reverse voltage means like this, right? It has to withstand Vm voltage across it, meaning across the diode we are applying reverse voltage to it around minus 32 volt, and it has to withstand that. Yes or no? So if the diode doesn't break down, then it's a good diode. So PIV rating is the peak inverse voltage of the diode, okay, that with which the diode can safely operate. The maximum reverse voltage you can apply to the diode under the conditions under which the diode can safely operate. So here the PIV rating of this diode is minus Vm. It can handle minus Vm voltages. Now imagine if you have not applied the transformer, you would have got over here minus 230 volt. Yes or no? Now because of the transformer, the AC voltage is stepped down to from 230 to 23, minus 23, let's say, minus 32, let's say. So it can handle minus 32 volts peak value. समझ में आ रहा है what I am saying? So it's the peak inverse. Let me write it down. Peak inverse voltage of a diode. The maximum reverse voltage a diode can withstand without damaging itself. Okay? Yes? So during negative half cycle, what happens? The output is 0. Yes or no? Current is 0. So output 0 will be shown by this. See? Output is 0 during negative half cycle. And positive half cycle में क्या होता है वापस से? Again the output becomes follows the input. Here it is. So that's why you get a, this is half wave rectified output. Now we will be drawing this waveform, but yeah, this is what happens. So now next write down, are you following what we are doing over here? Yes or no?
Yes,
Yes,
sir.
sir.
Okay. Now we draw the input output waveform. So leave a open a fresh page, write down, new page, input output waveforms. So V out is equal to Vi, which is equal to Vm sine omega t for 0 to omega t to pi, and it is 0 from pi to omega t to 2 pi. These are the conditions, mathematical condition. I'll explain, don't worry. So first let's draw Vi. Okay, let's talk about Vi. What is Vi called as? It's the AC mains voltage or the secondary output voltage. Hello, what is Vi? This is Vi, right? But what is Vi? Secondary voltage. Secondary voltage of transformer. Okay, this is pi, this is 2 pi, and this is 3 pi. Alright, now tell me, help me plot the value of the diode output voltage. How will it look like? So as I have already told you all, it will exactly look like a replica of input in the positive half cycle. So in the positive half cycle it will follow it. Negative half cycle it will be 0, right? I told you all that. We have seen just now. And again in the positive half cycle it will follow the input. Correct? So this is my signal. This is my uh, output V out. So we call it half wave rectified output. So this is V out, which is called as my rectified output. Now if I want to plot the current, then how will I plot the current? What nature will be the current waveform? Can anyone tell me? Now this is challenging. नेचर कैसे होगा करंट वेवफॉर्म का? It's a resistive load. I'll give you the hint. See, I out is, if I see the output here, I've written I out, right? Somewhere, see this written. I out is V out upon RL. Since it's a resistive load, the relation between V out and I out is linear. Okay, so nature will be same, because I out is just V out divided by some number, that is RL. So V out upon RL. Yes or no? So that's why the nature will be same. Maybe the height which is reaches is different. So here it is. Let me use a different color. Let me use green. Here the nature will be same. It will be positive over here. It will follow the same nature. But this height, what will be this height now? V out upon RL. This will be different, of course. It's a voltage upon resistance depending upon RL value. Now, if I want to plot diode voltage, ये कैसे दिखाऊंगा मैं? This is most challenging. चलो, if someone helps me out with this, then well and good. Tell me. So we have to go back to this I am plotting now VD1. Okay, I have to go back to my circuit. Now forward bias में what is my diode voltage? ये diode के across voltage कितना है मेरा? VD1. We are assuming it's a short circuit ना? So what is the diode voltage? Tell me. 0. Yes or no? And during the negative half cycle, what is my diode voltage? We have found out VD1 is minus Vm. Agree? Are yes or no? So in forward bias, in forward bias it's 0. In reverse bias it goes up till V minus Vm. Okay, and forward bias again 0. Understanding? So this value is minus Vm. This is my voltage across the diode. Okay, and the PIV rating of D1 is minus Vm. Okay, so these are my, please write it down, half wave rectified, half wave rectified input and output waveforms. Input output waveforms. तो ये हो गया second part. First part was the working and the explanation. Second part is the input output waveform. The third part will be the analysis to find the V out average, V out RMS, rectification efficiency, and ripple factor and other stuff. Completed this? Yes or no? Hello.
Yes, sir.
Okay. So next will be, and I hope you have understood this, how this has come. Okay. Now next will be, we will be doing the analysis of half wave rectifier. This has become mathematical. If you love mathematics, now this is the analysis of half wave rectifier. That means we have to derive first expression for V out average. Okay. Next, the expression for V out RMS. Third, the expression for ripple rectification efficiency. Then the expression for ripple factor. We'll find this. Then TUF also we have to find out, but that we'll find at the end together for all three. Transformer utilization factor. So this we will find in today's lecture in the continuation, which is lecture number 36. Will soon start now. So this completes 1 hour almost. So I'll stop the recording.